understand, like I don't like shorts until I came to like the Midwest. Now I'm like, oh my God, I understand shorts. I need shorts. All right, cool. There's the live stream and hello.
All right, cool. Now we just missed the shorts guy. I hope the shorts thing like cuts in where you go like, I never understood stores. Sure, until Kubernetes.
All right, I'll go ahead and get started and I'll pull you guys up.
Sweet.
Cool. You guys want to sit over here or?
Stand.
All right, perfect. Yeah, that works. Oh yeah, let me see. Can everyone hear me okay?
I don't think it's on.
Can you guys hear me okay? All right, let me try to adjust this mic. All right, hopefully that's good. Okay, let's get started. I'm really excited about the turnout here. Thank you all for coming today. My name is Saad. I'm a software engineer at Google. A little bit about myself. I work on the Kubernetes team in Google Cloud. I started before the project went to 1.0, and I got lucky enough to land on this team, and it's kind of skyrocketed since. So, very excited to be here. Fun fact about me: I've moved offices 10 times while I've been at Google for 4.5 years. We move around a lot because the teams continue to grow. To be fair, oftentimes it's changing floors. It's not necessarily changing buildings, but I have changed buildings, I think, 4 or 5 times. So I wanted to introduce some of my colleagues who are here today. We have Nick over here who works on the Gmail team, so if you have any Gmail bugs, please come and yell at him. We have Sam over here. He's also on the Google Cloud team. He works on identity. And finally, we have a couple of folks here who are going to help me with the presentation. We have Andrew, who's with the university program. Andrew, do you want to say a few things about yourself?
Yeah, so I'm on the university programs team. I'm based in the Chicago office, and I specifically cover tech-related roles at U of I. So you'll probably see me around a lot for ECS events, hanging out outside ACM, and doing a lot of different things. If you ever have any questions, you see me on campus, Google-related, I'm happy to help. My fun fact was that I've never had antibiotics. I saw Mahir's fun fact about the milk before cereal. I just kind of panicked. There's a lot of pressure. That one's a pretty neat one. So. But yeah, if anyone ever has any questions, we have an email alias specifically for UI/UC students that are interested, have questions about applications, interviews, anything like that. That'll be up on the slides later, so pay attention for that. And if you ever have questions, you can shoot us an email there, and we'll make sure to get back to you.
And finally, Mahir, who's been helping tremendously with this talk so far. Mahir.
Hi, everybody. I'm Mahir. I'm currently a sophomore at UC Computer Science, and as Andrew was mentioning, I put milk before cereal. Don't complain, just don't lie until you try. Okay, it's pretty good.
All right, thanks a lot, Mahir. So let's go over the agenda really quickly. First up, we're going to have a small presentation by Andrew. We're hiring at Google, and he'll tell you all about what we're looking for. Then I'm going to quickly introduce what Kubernetes is. And then my focus is going to be about giving you a deeper understanding of Kubernetes. You're all at UI/UC. That means you're very, very smart, and you can figure out how to use Kubernetes. You can, find stuff online. What I'm going to try to do is try to explain to you the principles behind why Kubernetes looks the way that it does, so that you can get a better understanding of how it actually works. And then we're going to finish off with a Kubernetes workshop that's going to be led by Mahir, actually trying to, create a Kubernetes cluster and deploy a real workload against it. So with that, I'm going to hand it over to Andrew.
Cool. So for those of you that haven't RSVP'd, we have a sign-in link right here. For what this link will do is anyone that fills it out, we have a couple of supplemental follow-up materials for the workshop, for Google jobs, interviews, resume tips. I'm going to go the next I only have 2 or 3 slides, but they cover open roles at Google, how to get in touch with us, and a lot of great interview prep resources. So if you like the slides will be important, really good resources to have, and we're going to send them out to everyone that's filled out the form. If you like those resources, you can also email the alias I was mentioning before is uiucstudents@google.com. So that's what the RSVP form is for. So yeah, we're hiring, and this is a small, I'm not going to go into all the details, all of the links, the deadlines, and everything like that. google.com/students is where to find all these. The main point is that there are things at Google besides software engineering. There's site reliability engineering, there's tools and infrastructure, there's developer programs, engineers, there's a cloud tech residency program, so lots of different things. We'd like all this information. Like I said before, we'll send it out to everyone who's filled out the form and also anyone who shoots us an email. One thing I did want to highlight is the cloud tech residency program. This being sort of a cloud-themed talk for anyone that's interested. It's not as full-on technical as the software engineering role. It kind of has sort of a hybrid customer-facing aspect to it. Really cool opportunity to experience a couple different areas of Google. You have three-month rotations after a 1 month of training. So definitely check that out if you're interested. It's g.co/jobs/CTR. We'll take you right there. And this is on the previous slide too, so we'll be sending that out to anyone that's interested. These are the resources I was talking about. Things to get ready for Google interviews, to train up on certain concepts. The technical development guide is pretty good. The second one right up there. And then for anyone that wants to practice interview tips, we have videos, online resources, everything are pretty good, and a couple other recorded events. So that's it for me, and I'm going to turn it back over to Saad.
All right, thanks a lot, Andrew. All right.
Let's go ahead and jump into the meat of it. But before we start, I wanted to get a feel for the room and try to understand where you guys are. How many of you have heard of Kubernetes before? All right, that's a good amount. How many of you have used Kubernetes before? And how many of you have submitted a patch against Kubernetes? It's an open source project. All right, cool. So let's go ahead and get started. Before we go, I want to try to make you understand what's in it for me. That's the question that I usually ask beforehand, before I do something. Why should you listen to me? Kubernetes is quickly becoming the de facto way that workloads are deployed against any distributed systems environment. This could be in the cloud, it could be on-prem. So what that means is, regardless of whether you plan to be in industry after your CS degree or go to academia, most likely you're going to encounter Kubernetes at some point. So hopefully this talk gives you, a better understanding of a product that you're going to encounter throughout your career. And another thing to keep in mind is a tool that I like to use for learning. In general, just focusing on memorizing things or copying commands and that kind of thing doesn't really get you very far. You should try to understand at a deeper level why things are the way that they are. In order to do that, the first thing to ask yourself is, what is the problem that's being solved? So you'll see in this talk, what I try to do is introduce what the problem is, have you think a little bit about how you would solve that problem, and then talk about how we solve the problem and try to understand why. In that way you can kind of learn, and it'll just make it easier to stick in your head. All right, so let's start with Kubernetes. What is the problem that Kubernetes is trying to solve? So you have a cluster of machines. That means you've got a number of machines and you want to deploy some sort of workload on it. And a workload could be anything. It could be a web application that you want to run. It could be a machine learning batch workload that you want to run. It could be anything where you want to deploy one or more instances of some application against multiple machines. How do you do that? That's the fundamental problem that Kubernetes is trying to solve. So how did people try to solve this problem in the past? Way, way long ago, it was basically bare metal machines. So you literally had servers on racks, and each one of them was a physical machine with an operating system installed on it. And a cluster administrator would manage each one of those machines, ensure a specific version of the operating system was installed on there, and then coordinate the careful installation of the software packages that needed to run on these machines. So if you wanted to deploy your application, you would have to work very closely with this cluster administrator to ensure that your application didn't conflict with another application. They might have different dependencies. You might use one Java runtime. Somebody else's application might use a different Java runtime. You have to handle these conflicts. It was extremely painful and manual. And then along came virtual machines. They solved this problem to some extent because they offered isolation between different virtual machines. Instead of being limited to a single physical machine that shared all of its resources with all the apps, you could create multiple virtual machines on a single machine for the different workloads that you were launching. But this still has issues. Namely, it's expensive and inefficient because you've got this very heavy hypervisor layer in the middle. It's very slow to launch virtual machines, and they're very difficult to manage in general. You have to kind of predict ahead of time and pre-allocate the resources from the underlying machine, whether you're going to use them or not. So if your application requires 30 gigs of memory, but sometimes it requires 50, you got to make sure that you provision a virtual machine that has 60 gigs of memory, regardless of whether you use it or not, and that's pre-allocated and nobody else can use that. So it's a little bit inflexible as well. So after virtual machines came containers, and containers kind of revolutionized a lot of things. Containers you can essentially think of as processes on Linux. They are essentially processes, but Linux sandboxes these processes so they can't see each other. So effectively they kind of act like virtual machines, but they're much, much quicker. They can deploy as fast as any process. They can start up as fast as any process. And the other nice thing is packaging. So the file system for the entire container is independent of the file system for the underlying machine. What this means is that every container can have its own dependencies. So if you have some application that you wrote that has a dependency on a specific version of Java, for example, you containerize that application and you deploy it, and I deploy a different application with a different version of Java. I can create my own container. They can both run on the same underlying machine and not have any issues. So it's a very, very powerful concept for just making it easier to deploy applications on machines. But there are still challenges. What are the challenges? Namely, how do you actually deploy these containers? So if you're running a web service at scale, you're probably not going to deploy a single container on a single machine. You probably want a number of these containers running across a number of these machines. And what happens if one of those containers dies? Do you then write some scripts to monitor all the containers and then do something if one of them dies? What happens if one of the nodes that you deployed on the entire machine crashes? Do you have monitoring that's going to move that container somewhere else? And that's kind of the fundamental problem that Kubernetes aims to solve. Containers are a good building block, but we need another layer which manages the containers and allows you to effectively deploy workloads against nodes that are workloads that are containerized against nodes. So Kubernetes is a system for monitoring and deploying containerized workloads. It's a container orchestration system. The word itself is Greek. It means helmsman. That's why the logo is a little steering wheel or whatever. And it supports multiple container runtimes. Docker is the most popular runtime, but Kubernetes kind of works with a bunch of different container runtimes. And the nice thing about Kubernetes is that it's designed to work on any type of cluster. So if you have any collection of machines, you can deploy Kubernetes on it, and Kubernetes exposes a standard interface with which you can deploy your applications. So if you squint, Kubernetes is a lot like an operating system. What is an operating system? An operating system is a piece of software that takes the local resources that are available on a given machine, and it basically allows the applications to share them and not have to worry about interacting directly with the lower level hardware. Whereas operating systems are doing that for a single machine, Kubernetes is trying to do this at a higher level for a set of machines, a number of machines. So you could have a pool of machines, whether they're sitting in your closet in a rack, or they're running in the cloud on Google Cloud or on AWS or somewhere else. You deploy Kubernetes to manage this, and then instead of manually figuring out how you deploy these workloads, how you monitor them, how you move them around, you let Kubernetes manage that, and you interact with only Kubernetes. All right, so now you should have a rough understanding of what Kubernetes is. If you're interested in it, you can go and actually we'll do the workshop later today, and you're going to find out how to actually use it. So now I wanted to kind of talk about why Kubernetes looks the way that it does, and the first question I want to ask you is, if you have this system that will be able to deploy workloads for you, let's call it Kubernetes, how would you deploy a workload? The obvious answer is, well, I'll create some sort of service. It'll act as my API that my end user is going, that I'll talk to say, please, deploy a workload for me. And that service can then figure out where the workload should run and talk to that node and say, hey, please start this workload. Pretty straightforward. It basically just proxies that request forward. Can any of you see any issues with that model? So, well, one of the issues is what happens if that node crashes, right? So you've effectively launched your container, but now how do I make sure that this container remains running? If the container crashes or the node crashes, or if there was a momentary issue with that node and it missed that message and returned an error, what happens? With what we propose, that means you as an end user have to issue another command to say, please start this container. You kind of have to do everything manually. And this concept is basically what the first principle of Kubernetes is about. The principle is that Kubernetes APIs are declarative rather than imperative. What that means is that instead of issuing a set of instructions to the system on what it should do, what you do is you define the intended desired state, and the system continuously drives towards that state. So instead of saying, please do X, Y, and Z, you say, please make this happen. I want a container started and keep it running for me. And the system will make that happen. You can think of this kind of like an autopilot system instead of manually driving. You kind of set what your desired point is, and all the systems work together to ensure that happens. And so concretely, what does that look like for Kubernetes? Kubernetes has a API server, and you as an end user use a command line or a REST API or a UI to issue commands against this API server. And you, in order to deploy a workload, you basically create a configuration file that looks something like this, that describes what your container, what containers you want to run. In this case, an Nginx container. And you pass this over to the API server. And when you do that, the API server actually persists your pod definition on the API server, as it's basically like a file that's saved on the API server. And the nice thing about that is that effectively what this means is you don't have to reissue this command. Once Kubernetes has scheduled your workload on some machine, if something bad happens, one of the benefits of this approach is automatic recovery. If that node goes down, Kubernetes knows, well, I know what's supposed to happen. I'm supposed to have pod A running, but something happened to node B and my pod's not running. So let me go ahead and move that workload somewhere else. And this doesn't require any intervention from you as a user, so you remain happy, no more sad faces. So the next problem is, okay, now you have this nice interface to interact with Kubernetes. How does Kubernetes interact with its nodes or other components that make up the Kubernetes system? So, for example, you created your pod definition. Should the master basically call out to the nodes to say, hey, you should start this container? That is an obvious solution, and that would work. But there are drawbacks to this, and the drawbacks are that the master basically has to keep track of every single node and what it has scheduled to that node and what the current state of that node is, and it has to basically, if one of these nodes crashes, it has to catch that node up, right? So if there was a node that was supposed to be running pod A, and that node crashes, the master has to be able to understand that and issue follow-up commands to be able to allow that node to recover. So recovery is an automated process that's all part of the master. And what that means essentially is that the master becomes very, very complicated, one. And the second challenge is that it becomes very difficult to extend the master because every component, most of their logic is essentially embedded in this one master component. So is there something better that we can do here? And yes, there is. So this is the second principle of Kubernetes, that the control plane itself is transparent. There are no hidden APIs. So the same public API that you use to interact with Kubernetes, the Kube API server with a declarative API, is the same API that all the components within Kubernetes use to interact with each other. They never interact directly with each other. So the master never talks directly to a node. Instead, it talks to the API server, and all the different components, including the nodes, monitor the API server and figure out what they're supposed to do. So everything watches and reacts to the API server. What does that look like? So we're going to introduce a new component here. So you've got your master over here, which is what you talk to as a user. But your nodes and any other components that exist in Kubernetes are all watching the API server to figure out what to do. In this case, the scheduler is a component that will figure out where your workload should be scheduled, which machine should it go on. Given I've scheduled something on node A and I have certain constraints for how much resources node A has, where should I put the new workload that's coming along? The scheduler makes that decision. So in this system, when you create your pod A, that gets persisted on the master as a configuration definition file. And then all the components are watching it, so they see this new pod object get created on the API server. And so the master scheduler says, okay, I see that there's a new pod that currently is not scheduled. I'm going to run my algorithm to figure out where is the best place that I can put this workload. It decides that node B is the best place for this pod, and so it doesn't actually talk directly to node B. Instead, it just updates the pod definition file on the master API server to say, hey, by the way, I have determined that this should be scheduled to node B. That's it. All it does is read the API server and talk to the API server. And now node B basically I'm missing a slide here, but node B is also watching the API server, and it will realize that it should be running the pod B workload, and it'll go ahead and get that started. So what is the benefit of this API, or of basically having a transparent API that's declarative instead of imperative? The biggest benefits are around making a more robust system. So any single component can crash and your system can continue to work. So for example, if the master crashes, the nodes can continue to operate independently and keep their workloads running. So node A, for example, knows that it's supposed to be running pod A. If the master crashes or goes down for some time, it knows I still need to keep this thing running and can operate independently. The other major benefit of this type of approach is that it makes everything more composable and extensible. So for example, if you don't like the Kubernetes master, you can actually swap it out. I lost track of my slides. Hang on, sorry. Right, so no hidden internal APIs. The benefit is you can swap out components. So for example, if you don't like the Kubernetes master, you can swap it out with your own custom scheduler. And the reason that you can do that is because the API is completely transparent, and it's the same API that you use to interact with Kubernetes. So if you want to create a custom scheduler, all you need to do is write a component that interacts with the public Kubernetes API, and then disable the default scheduler that ships with Kubernetes and launch your own. And so effectively now we have a system that's more robust, more composable, more extensible. All right, so let's move on. Next thing is, I showed you how to run a very basic workload that is essentially stateless, meaning it doesn't persist any data. That's one thing to know about containers is that when a container goes away, anything that you wrote inside that container is also deleted, it's gone. So if you're trying to run a stateful application, something like a database, or you're trying to persist any sort of file, it's difficult to do just with containers. So the solution in Kubernetes is something called volume plugins. volume plugins are essentially, you can think of it as directories that are mounted inside the container that can persist beyond the life cycle of just that container or that pod. We have a number of volume plugins. So on the remote storage side, if you're familiar with things like NFS, Kubernetes supports that. If you're running in cloud environments, we support virtual disks like Google Cloud Persistent Disks, on Amazon, EBS block volumes, and a number of these remote storage options. In addition to remote storage options, we have a number of ephemeral storage options. And let's dive into a little bit more about what that means. Ephemeral storage is storage that has its life cycle tied to the pod. So similar to the file system inside the container, it's created when the container is started and it's deleted when the container is deleted. But the benefit of this storage is that it's shared between containers. So in Kubernetes, the basic unit of scheduling is not a single container, it's a pod. A pod can be one or more containers. And if you want to be able to share files between these containers, how do you do that? The way that you do that is through these ephemeral storage volumes. The basic ephemeral storage volume is an empty directory. It's basically a directory that's mounted into both containers so that if you write from one container, it's immediately visible from the other container. That way you can containerize different components of your application and they're still able to communicate with each other. And this is effectively scratch space that the two containers can use. So that's pretty nice, but we use this basic building block to build something more powerful on top of it. And we'll talk about that in a little bit. First, I also wanted to introduce you to data that's stored within the Kubernetes API. So we talked a little bit about the Kubernetes API. You use it to deploy new workloads, but it's very, very flexible. You can also use it to store information. One of the rules for containerizing applications is that you don't put in secret information or sensitive information inside the container. So think like your passwords, your certificates. Those things should never live inside your container. You should put them somewhere more secure. So Kubernetes offers you a way within the Kubernetes API to define secrets independent of your containers. In addition to secrets, there is also a way to define configuration information. So, your application may have a number of parameters that it accepts to change the way that it behaves. Ideally, you don't want that baked into your container because that would require you to update your container every time you want to change a configuration. So Kubernetes offers a way to be able to put this configuration information in the Kubernetes API instead of inside your containers. And then finally, Download API is a way to fetch Kubernetes-specific information. So now there's a problem with all of this. It's a lot of cool information that's sitting within the Kubernetes API. How does your application, which is running inside of a container, access this information? The answer is pretty obvious. We had the principle where the Kubernetes API is transparent and public and everyone can interact with it. So you simply modify your application to reach out to the Kubernetes API server and fetch the information that it needs. So when your application is running, it can make a call to the Kubernetes API server and say, I want such and such secret, and get that information back. But the problem with that approach is that it requires you to modify your application. So if you wrote an application that didn't understand that it was running on Kubernetes, you would actually have to modify your application, and we don't want to do that. What we wanted to do with Kubernetes was be able to run with existing workloads, just the current applications that you have, without having them realize that they're running on Kubernetes. We wanted the application to be essentially agnostic of Kubernetes. And that principle is called meet the users where they are. So the users don't want to understand Kubernetes. They just have applications that consume configuration information or consume secrets. Let them do that in the way that they're used to doing it. So effectively what we do is we allow this information, secrets and configuration, to be made available inside of a container as a file. So a lot of applications are able to consume both configuration and secret information as files, and with config map volumes, secret volumes, and downward API volumes, user can say, when this pod is running, please take this specific secret and mount it to this specific location inside the container. And the application running inside that container can now just read the file from that location. It doesn't have to understand anything about Kubernetes. So that's beautiful. Why do we care about that? Why try to minimize, or why meet the users where they are? And the goal there is to try to minimize the hurdles for onboarding onto Kubernetes. All right, now we're going to move on to the fourth principle. Before we get there, I want to talk about remote storage. So we talked about ephemeral storage. This is storage that was created when the pod is created. It's nuked when the pod is deleted. But if you want to persist data, if you want to have a database or something that stores images that your customers are sending you, how do you do that? If you don't want that stuff to disappear as soon as your container dies. So the best way to do that is to use some remote storage system. If you're running in an on-premise environment, you might have an NFS. You might have an NFS instance running. You might have some sort of software-attached network that's available to you. You might have some sort of network-attached storage. If you're running in cloud, there's a number of cloud options that allow you to store information remotely away from the local host. And that is the recommended way of persisting information inside Kubernetes. So assuming you have one of these remote storage systems available, the way to use it is pretty simple. In your pod definition, in addition to specifying what container you should be running, you specify the type of storage that you want. So in this example, we're going to use a Google Cloud virtual disk, and inside the pod definition you can specify, I want to use the Google Cloud persistent disk with this name, and when I deploy this pod on Kubernetes and GKE, Kubernetes will automatically do everything that it needs to make that storage available inside of the container. So I'm going to walk through that a little bit to reinforce some of the concepts we've talked about. So you as an end user created a pod object on the Kubernetes API server. The scheduler, of course, reacts to that by saying, hey, I noticed that there's a new pod object and it's currently unscheduled, so let me go ahead and schedule it. So it finds an appropriate node for it, and it updates the API server object with a new field that says, okay, I've scheduled you to node 1. Now we're going to introduce another Kubernetes component, if my slides. This is the one, yeah, perfect. This component is called the attach-detach controller. There are a number of controllers in Kubernetes, and what these controllers do is they watch the Kubernetes API, and they figure out what they're supposed to be doing, and they look at what's actually happening, and then they take action to try to drive the actual state towards the desired state. One of these controllers is called the attach-detach controller. The attach-detach controller's purpose is look at pod objects, look at the remote storage that they have, and figure out if there needs to be any actions taken to make that remote storage available on that given node. So in this case, immediately after this pod was scheduled, the attach-detach controller goes, I see that it's referencing a GCE persistent disk. Let me make sure that that GCE persistent disk is available on node 1. So that attach-detach controller issues a command to the Google Cloud backend and makes the Google Cloud persistent disk available on node 1. And then node 1 has an agent called a kubelet that is also watching the API server. It says, oh, I'm supposed to be running pod A. It talks to the local Docker daemon, and it starts that container, and it realizes that the GCE persistent disk, which is now available on node 1, needs to be mounted inside this container. So the kubelet ensures that that disk is available inside the container. So when the container starts to run, it now has a remote cloud persistent disk mounted at a location inside the container, so when the application writes to that directory, that data is persisted. So now if the container goes away, the data is persisted on this remote disk, and if the container comes up somewhere else, the data follows it. So this is a basic mechanism for allowing the storage to follow wherever the data, or the data to follow wherever the compute gets scheduled. So it's a very, very powerful construct in Kubernetes. All of this happens automatically for you. But there is a challenge here. The problem with this is that you lose portability. In your pod definition, you specified that you wanted to use a Google Cloud persistent disk. The problem is that pod definition file now is specific to Google Cloud. If you take that pod YAML file and you move it to an Amazon cluster running Google Cloud, or running Kubernetes, it's not going to work. If you move that pod file to a local cluster that you have running Kubernetes, it's not going to work. And the reason is because that pod file says this pod is going to use a Google Cloud persistent disk. So how do we work around that? The way that we work around that is a couple of new Kubernetes API objects called persistent volumes and persistent volume claims. The purpose of these is to decouple the consumption of storage from the implementation of storage. Let's talk about what that actually looks like. So, we've seen the pod objects on the API server. It's fairly straightforward. It says, this is the container I want to run, and here are any dependencies that it has. Now we have a couple new objects, the persistent volume claim and a couple cluster administrator objects. So now instead of specifying directly inside your pod that you want to use a Google Cloud disk, what you say is, I have this PVC, generic request for storage, and you reference that PVC. And inside your PVC, instead of saying, I want a Google Cloud disk, what you say is you describe what type of storage you want and how much of it you want. So you say, I want read-write-one storage that's 20 gigabytes. You never say anything about the specific type of storage. And your cluster administrator, the person who sets up your Kubernetes cluster, also creates an object called a storage class. Inside the storage class, they define what type of storage system is used to fulfill your request. So when a new request for storage comes along, the storage class basically defines what the type of storage should be used. So in Google Cloud, we set the storage class to say use GCE persistent disks. So when you as a user create a new PVC object, Kubernetes looks at the storage class. It says, I'm supposed to use Google Cloud persistent disks. Let me go create a new Google Cloud persistent disk and automatically create a new PV object to represent that. And as far as you're concerned as a user, the two objects that you have are completely agnostic of the underlying storage. The benefit of this is now if we take this and we move it to a different cloud environment, let's say to AWS. Let's go to the next slide here. There we go. So now everything remains the same. The only difference here is the cluster-specific objects that are invisible to you as an end user. In this case, my Amazon cluster administrator said, when somebody requests storage, use an Amazon EBS device instead of a GCE persistent disk, and all of that is invisible to you. And the way that you deploy a workload against Kubernetes remains consistent. And that is the last principle of Kubernetes. It's workload portability. And this is the most important thing. If you take away one thing from this talk, what is Kubernetes about? It's about workload portability. It means that the way that you deploy a workload against a cluster is going to be consistent regardless of the underlying details of that cluster. Whether you're running in one cloud environment or another cloud environment or on-prem, you as an application developer have this consistent API. You just describe how you want your application to run, you tell Kubernetes to do it, and Kubernetes takes care of the rest. And that is the power of Kubernetes. It allows you to not have to worry about the underlying cluster. You just have this consistent interface, and it's repeatable, and it's reusable, and it's a lot like an operating system where you don't worry about the underlying hardware, you just make sure that your application runs against this operating system. As long as the operating system is available, your application is going to run. So to recap, the 4 principles of Kubernetes that we introduced were, number 1, Kubernetes API is declarative over imperative. What is the benefit of that? Anybody paying attention? Anybody? Yes? Exactly. Right. By being declarative, you don't have to constantly monitor this system. This system automatically corrects itself. It's like an autopilot system. Number 2, no hidden internal APIs. What is the benefit of that? Yes?
It's easily extensible.
Exactly. By having no internal APIs, it becomes very easily extensible. You can swap out components very easily. Number 3, meet the users where they are. Why? Yes?
More liberally in the sense that like the user doesn't have to change their own like programs in order to run on the system.
Yep, that's a good one. Any other reasons? Okay. I'll go back to this one. So meet the users where they are. Basically, your application doesn't need to be changed at all. Well, it's just, yeah, it's backwards compatibility. It's, you don't have to modify your application to be aware that it's running in Kubernetes. You can take an off-the-shelf containerized application, deploy it in Kubernetes, and it'll just work. So it just lowers the overhead and burden of deploying on Kubernetes. And the 4th one is workload portability. Why? Why do we care about this? Yes? Exactly. So you're going to be able to deploy your application the same exact way regardless of what underlying platform that you're running on, and that's it. That's the beauty of Kubernetes. Last slide here is a workshop demo by Mihir. So I'm going to hand it off to Mihir. Thank you very much.
Thanks. So first, I just wanted to say thanks to Saad. I know that when I started learning Kubernetes, these concepts aren't the easiest to kind of figure out. And it did take me a while to kind of understand all these concepts. So, you guys basically got an hour crash course, and I have a couple links that I use and that I refer to as my Nutanix Bible. And now, I guess you guys have found your Nutanix Bible. Sorry, Kubernetes Bible. So, thanks, Saad. So I'll give him a round of applause, please. Okay, so now I'm going to take you guys through a quick deployment. Oh, thank you. Is this on? Oh, it's fine. I can just talk loudly. You guys can all hear me, right? Yeah? Okay, cool. So I'm going to take you guys through a quick deployment exercise. So if you guys can all on your computers go to this link right here, tinyurl.com kns-experience.
Is that hot?
So if you have GCP credits, that's fantastic. You guys should all log in and go to your GCP console right now. If you don't, you should definitely go to this cloud.google.com /free link. Basically, it lets you get some free GCP credits to access a cluster and basically play around with it. So go to that and sign up for it. I'll just go through this kind of quickly, and then you guys can all stay back and then create your own clusters and start running it. And we'll have some people walking around helping with that in case you need help. Usually we run other basically Cloud Shell lets you do all this in your browser and has all of these tools already implemented. So it's very useful and very helpful. So basically, this is kind of straightforward. This line right here is going to create a cluster for you. And this line will take a little bit of time. So that's more or less straightforward. So basically just making a cluster and using the Google Cloud Engine. And this will take a minute to kind of spin up. Just a quick question. Have you guys heard of kubectl? Yes, no, maybe so. Okay, so a lot of people kind of ponder over this big question: is it kubectl or kubectl? Any preferences? kubectl, kubectl? Okay. Well, I guess kubectl it is. I guess I've been saying wrong all this time. So what we'll be using to basically deploy this application that we're going to be using is, so the application itself is called Rocket Chat. Basically, it's just a chat service. The platform we're going to be using to help deploy Rocket Chat is Helm. And basically, when you're deploying applications, a lot of times you have services basically allow you to access different pods, and a variety of services you can use to kind of deploy an application. You have services, you have headless services. You have to create persistent volumes and persistent volume claims as Saad was talking about. So basically, Helm helps you kind of automate all this stuff, and it does all these processes for you. So it makes it a lot easier to basically deploy applications. So any questions on what Helm is? Oh, yeah, can you see the instructions right now? Or should I make it bigger? So as you can see, the cluster, which is called Rocket Chat, has been made, and there's 3 nodes right now. So basically, we'll go ahead and we'll download the Helm binary. And that's been installed. And then we will unpack it. Basically, the utility of this line, the next couple lines, is essentially just making service accounts, which allow Helm, Pillar, which is the service side component, which basically helps with deployment, and basically creating a couple service accounts which allow you to easily make the application and have access to all the namespaces and things like that. So basically, this is where we actually initialize the Helm service, and then we're going to update the charts, basically pull all the most recent charts that Helm has. And now this is basically a values file. So basically in Helm, there's basically one main chart file which you can use to basically run applications, which is generally called values.yaml. And this has most of the important information, like basically what kind of storage you're using, the storage class name, important information like that. You can also talk about how many replicas you want and things of that nature. replace the file that we just downloaded with the file that we had originally. So now we're going to go in and actually change the storage class name on the values.yaml file. So we're just going to use vim. So you can see here's just some configurations, like for example, image, jet, 156. Persistence, this is what's on top. We're using persistent volumes instead of just, standard volumes. So basically persistence of subordination is less if the data persists and it will just leave when the positive. So here, storage class, we will edit that. So on GKE, a storage class is already initialized for any person that you might have, and it's called standard. So that's why the storage class is called standard. So we'll go back. So yeah, add the values.yaml button to the GKE storage class name. And then this is basically just to install the actual that's basically just to install the application. So as you can see now is when the application is actually made. And these charts are very friendly in the sense that even if you don't do much of the application itself, it gives you a lot of options and it tells you a lot of nitty gritty things to edit the application, change it, and add additional functionality. So if you look at the bottom of the experience walkthrough doc, you can see some pretty interesting things about how you can learn more about the application itself. So right now we're going to use kubectl get pod to see if the application is up and running right now. As you can see, the MongoDB database has been instantiated, and then Rocket Chapter containers are being created. So right now, what this has done is basically made the application inside the cluster, but it's not accessible. It's not accessible by anything outside the cluster. So what we're going to do right now is we're going to actually use kubectl edit SVC. So SVC is just a short form for service. So a lot of these things like pod, service, deployment, they all have short forms, which I encourage you guys to learn if you guys want to save yourselves a few characters here and there. So edit service, and the application name is test. So test-rocket chat. And here you can see the type, so basically if an application is deployed only in the cluster itself, then it's cluster IP, which basically means there's an IP, there's an internal IP for the cluster, but it's not accessible from anything outside the cluster. So there are a number of ways to deploy or to expose an application to outside the cluster. The method that we're going to use right now is basically using load balancer. There's also Ingress, which is a very popular tool for some people. So what we'll do now is we'll check the service. Well, actually, let's check the pod first to see if it's running. So yeah, as you can see, it's running now. So this gives you a lot of health information. So basically, you can see the name itself. You can see that the pod is ready. So here, initially, when it wasn't running yet, you could see that there weren't any pods that were accessible. So basically, for example, the service, the test rocket chat service, right? It forwards requests to the test rocket chat pod. But if there are no pods that are ready, no pods can take the requests. And you can also see information about restarts, and how long they've been instantiated and things like that. Restarts, that's generally something that most people don't want to deal with because that means that something's wrong. So the fewer the number of restarts, the better. So let's check the service. can see here now, the Rocket Chat application, Rocket Chat service has been exposed, and there's now external IP which you can access to, that you can access to basically take requests and things like that. So let's just check that really quickly. That was external IP, and then it's at port 3000. It's loading, I promise you guys. So can anyone tell me a problem with the setup right now? Yeah, so I'm just testing it from port. So can anyone tell me a problem with the current setup? So there's one pod for the test Rocket Chat, for the Rocket Chat application, there's one pod for the MongoDB database. It's not accessible, right? So if one pod goes down, right, there's no way that you can actually access the application. Okay, there we go. Yeah, so as you can see now, the application's been deployed. You can access it on your browser using the external IP and the main port. So yeah, so the problem is that it's not really too accessible because you only have one pod for your application running. If that pod goes down for any unforeseen reasons, the application is basically down. So what you're going to do now is you're going to scale the service or scale the replica set. So basically, we'll use kubectl, scale, replica set, rs. Actually, let's get the names of all the replica sets. Yeah, so you can see you have the test MongoDB replica set and the test Rocket Chat replica set. Let's copy paste this because I have no replicas. And we'll do 3 just for convenience sake. So as you can see now, the replica set has been scaled. So let's do this. Oh, oops. Yeah, so this application uses deployments, not replica sets. Or it's based on the deployment, not the replica sets. So we'll actually be scaling the deployment. So as you can see now, the deployment itself has been scaled. And if you look at the pods, two additional containers being created, which basically are the 2 additional applications that the 2 additional replicas that you have asked me to instantiate. So as you can see here, this is basically what tells you how up to date your applications are, or your deployments are. So you can see here, for test Rocket Chat, you want 3, and you have 3 at the moment, right? But if you delete one of the pods, right? Say delete this one. And you get deployments. Oh, I guess it didn't update the time. But yeah, I guess Rocket Chat. Okay, Rocket Chat comes back pretty fast because I guess the application isn't as applications, you would still have desires to be current is 2 because you just killed the pod. And basically, it's a good way to kind of keep track of applications you have, how many you're running, and kind of what the status is on the cluster. So any questions? So that's yeah. Creating what? Yeah, so not the website itself, because it's basically exposed from external. It's being exposed by the service. Basically, you use a load balancer, which basically exposes the ports and creates an IP address. So basically, exactly, it makes sure that the application is always accessible.
Yeah, so to expand on that just a little bit more, the question is, does that help scaling it out? Does it help the website not go down? And you have to look at it from for each application. In general, what you do is try to look at all the different types of failures that can happen. So if I was running, one instance of the Rocket Chat application, what's going to end up happening is that's going to run on a single machine, and if something happens to that container or something happens to that machine, your website is effectively unavailable. So ideally, you want your fault domains to be more than a single machine. So you would run with a replica set of 2 or more, and you would also specify that I don't want the additional replicas to land on the same node, so that if something happens with that node, it effectively doesn't affect your service. And so Kubernetes automatically handles that for you. So for stateful or stateless applications, it's very simple to do. For stateful applications like MongoDB, it becomes more challenging because the data tends to be stuck in one place and is not necessarily not necessarily available in multiple places at once. At that point, you have to look at your storage system and whether it does, things like multi-reader or do some sort of replication at your application level. You have to look at that particular application, basically. But good question.
I was going to say also the other thing that you can do is you can use various other data storage options. I believe data store supports basically multiple readers and it's highly scalable. So if you don't mind outsourcing your data storage to some sort of like hosted or managed service, sometimes you can do that instead of sort of running your own.
Any other questions? Yeah, well, that's basically a quick crash course in using Kubernetes on DK.
And the other thing is, so a lot of these steps here are just setting up Helm. If you'll look, there's basically one line to actually deploy the Kubernetes cluster and one line to actually deploy the application. Helm you can think of as a package manager. So instead of manually constructing the configuration files and deploying manually everything against Kubernetes, Helm packages a bunch of configuration information together. And so a lot of these steps are actually you installing Helm, which has a server-side component and a client-side component, then giving permissions to Helm to be able to deploy against your cluster, and then finally using Helm to deploy this application. Think of it as a package manager. And then once the application is deployed, with the steps that Mihir ran at the bottom, you actually get to look under the hood and see what's going on. So Helm basically launched a couple of pods, and then they were deployed as deployments, and then he was able to scale it out by talking directly to Kubernetes instead of going through Helm. So give it a shot.
Yeah, sure.
I mean, everybody else give it a shot.
Oh, yeah.
And let us know if you have any questions. We'll be walking around, and maybe you can put the link to the instructions up.